Now, the first thing I want to do is motivate why we might care about synthesizing MapReduce programs in the first place. We live in an increasingly data-driven world. Over 90% of the world's data has been produced in the past 2 years at a rate of approximately 30 terabytes a second. Furthermore, a lot of this data that we're producing is incredibly personal. The majority of Americans have smartphones and have surrounded themselves with sensors. We saw in Ben Zorn's keynote the other day that we now have the Internet of Things enabled light bulbs and forks that are all gathering data on us and feeding it back into our personal lives. With that being said, though, large-scale data analysis is still not accessible to the average consumer. In the past, there have been efforts to lower the barrier of entry for doing large-scale data analytics. We've seen tools like MapReduce, Hadoop, Spark, Flink, Myriad, Disco, all these other options and more that all allow you to construct very scalable data analysis or data parallel programs. Just as a quick overview, I want to give a quick outline of how the typical MapReduce program typically operates. On the left-hand side, you can see we're given a set of input data. This gets mapped by a mapper function, transformed individually before being fed into a shuffle phase. Now, the shuffle phase is usually a sort of a black box optimization that's moving memory nodes around in the network and doing what it can to optimize the performance of it as much as possible. So we usually treat this as a black box, although here it's a white box. And then once we have the output of the shuffle phase, we feed this into a bunch of reducers that are aggregating the data together into a single value. Now, it's important to note that all of the tools that I just showed you their logos of on the last slide don't necessarily operate exactly in this way. It's not necessarily just a single map followed by a single reduce. They may have like a map followed by another map, or a map followed by a filter and then followed by a reduce. But this gives you a general view of what a data parallel pipeline might look like. And with that in mind, we've introduced the tool Big Lambda. Big Lambda is a method for synthesizing data parallel programs from input-output examples. So the end user would be able to provide an input-output example, a couple of instances of the original input, and what the output should be, and Big Lambda will churn away for a little bit and will produce a data parallel program that is consistent on this input-output example and will scale to running on even more data. Now, there's a few challenges that we face whenever we're trying to synthesize a program like this. The first is non-determinism. I mentioned before that the shuffle phase we sort of treat as a black box. It's very difficult to reason about because it's very dependent on the state of the network at any given point in time. In fact, if you don't design your program carefully, when you run it with the same inputs, you may get different results based on the output of the shuffle phase. This means that our functions are not pure. The programs that we're synthesizing are not pure, and we would like this to be the case. So whenever we are synthesizing our functions, we will ensure that they are deterministic with respect to this non-determinism introduced by the shuffle phase. The second challenge that we face is that we're dealing with a huge variety of domains. People who want to do data analysis are dealing with things like tweets, they're dealing with sensor data, GPS data, wiki logs, whatever the smart fork data gives you. And so we'd like to be able to have this synthesis parameterized by APIs so that if some new data paradigm comes along, we can just immediately extend it and still maintain all the power of the synthesis tool. Now, the last and most important problem that we have is that the search space is very, very sparse. If you imagine the set of programs and then you go and you circle all of the data parallel programs, you're going to find that they are very few and very far between. And with this in mind, we are going to syntactically bias our search towards data parallel programs. And we do this using something called higher order sketches. These higher order sketches are well-formed but possibly incomplete programs that are made of these data parallel combinators. If you're familiar with the Spark API, these data parallel operators probably look very familiar to you. Now, you can think of these sketches, these higher order sketches, essentially as a program that has holes in it, and these holes have different shapes. And it's our job during the synthesis procedure to fill in these holes with the appropriate shape. Now, so far, everything I've talked about has been fairly abstract, so we're going to walk through a quick example of a possible use case. So let's imagine the average user, Bob. Bob has a Twitter account, and he has some questions that he wants to ask. He's able to gather a whole lot of Twitter data, and he wants to work through it. So maybe he's curious as to how popular he is, how many times his handle actually appears, or maybe which of his friends is using the most hashtags. So the first thing we need to do is parameterize the search by the API. Bob knows he's dealing with tweets, for example, so he might pick some functions from the Twitter API, or he might just pick the entire API as a whole. So this allows us to deal with things like the contents of a tweet, the author of a tweet. We're talking about users. We have methods for extracting particular hashtags, for example. But he's also going to pick an API that is very general and can be applied to a large variety of domains. And this usually consists of functions like pairing and taking lengths of sequences and maps and filters. Now, it's important to note that the map and the filter here are not the same data parallel map and filter from the sketches. These are sort of the standard like functional operators that we use just for for constructing the individual functions. Another thing I want to point out here is that when I said sequences earlier, I don't actually mean sequences as maintaining an order. Typically, whenever you're doing anything with a large number of values in a MapReduce style program, the shuffle phase is going to be returning things in an arbitrary order, and it's very difficult to ensure that things are arriving in the order that you would expect them to. So we're not able to rely on this, and so we abstract this away just by using multisets, which is essentially just a list without an order associated to it. So back to our example, Bob probably picks a few tweets that he has, and he's going to annotate these and come up with his own solution. So he's going to sit there, and he knows how to do this by hand. All he has to do is look and count the number of hashtags, and then find the user associated with the tweet that has the most hashtags. And he'll construct this as an example. So now we'll look at a solution that Big Lambda would synthesize. We'll start with a sketch, which is just a map, followed by a reduce, followed by an application of an arbitrary function. There's a few moving parts here, so we're going to walk through it step by step. The first thing we do is apply a map. This is transforming every element independently. Now, this map looks a little bit complicated, but all these functions we've seen before from the API. We're pulling out hashtags, we are counting the number of hashtags, and we're just pairing it up with the author. From here, we need to reduce it down to get a single value. We need to aggregate all this data together. So the reducer we're using in this case is taking the lexicographic max of the pairs. So 4 Bob is greater than 2 Alice, which is also greater than 3 Claire. However, we have to deal with the shuffle phase. We may not necessarily be evaluating these particular pairs in this order. It may be this order, or it may be this order. Each of these looks a little bit different, but the end result is still always the same. Now the reason for this is because max is both associative and commutative, so it doesn't matter how we structure this parse tree. Although we'll see later that sometimes this can be an issue, and I'll talk more about that at the end of the talk. Now finally, we're going to apply one more function, which is going to take our pair and is going to extract the critical information that we care about, which is Bob's user, and return it. So this is the program that Big Lambda would synthesize from Bob's simple example. We've already seen how he actually parameterizes the search. He provides a set of examples, he provides a set of API functions that he cares about, and he provides a sketch, maybe 1, maybe 2, maybe more. Typically, our synthesis uses 8 total sketches. And then from here, we can move on to the synthesis phase. I'll show you how we actually find these programs. So synthesis operates on a producer and consumer model. These higher order sketches act as the consumer, which are pulling solutions from the producers and combining them to form total programs. To find these subproblems, what we need to do is take every single sketch that we have and evaluate it in the context of the examples to infer the types of the holes to find out what sort of programs we need to actually fill in. So in our previous example, we saw that Bob was dealing with a multiset of tweets and he wanted a user at the end. So the end function that we're looking for is going to map a multiset of tweets to a user. And when we do type inference, we find out that the types of each of these holes are as follows. We have the mapper is intending to take a function that maps a tweet to some arbitrary value alpha, or to some arbitrary type alpha. The reducer is going to combine 2 alphas to give us back another alpha. And then the application is just going to transform that alpha back into a user. In this case, the examples that we saw, the alpha was a pair of integers and users. So now I want to talk about how we actually start generating solutions of every single type. This is a fairly straightforward technique. It's a top-down, type-driven enumerative synthesis, where we start with a program, or a function in this case, that is intending to take in a tweet and is trying to return us some particular value. We don't know what this value, or what type this value is right now, because we have an unknown type constant, an unconstrained type constant. So what we do is take a look at every single function that we have in our API and try and refine this a little bit as possible. This branches out our search space a little bit. And so typically what we'll try and do is explore the search space by some heuristic function. Just like machine learning, we want to bias towards simpler solutions to prevent overfitting. Here we typically do this by trying to pick the smallest functions, although we've been playing with other ways of picking the heuristic to get some interesting results. So what we're looking for in the search tree is ground programs. That is, programs that no longer have any holes in them. We're looking for things that don't have any shapes. And on this page, you can see that we have 2 examples. We have the function that takes in a tweet and just returns 0. And we have the function that takes in a tweet and returns the author of the tweet. One of those is probably right, or maybe we need to continue searching down through the rest of the tree. Now that we actually have our producers that are generating all of these ground programs in order according to some heuristic, we need to combine them with our consumer. And so to do so, all we do is consider every single producer, iterate over the list, and the consumer will do a frontier search over the Cartesian product of every single one of these lists. Now, it's important to note here that we get a nice benefit that each of these producers is operating in parallel. So we can offload a lot of this work to other cores if our machine has that capability. This also has the nice benefit of decomposing our problem into a lot of synthesis subproblems. And this actually helps us for a variety of reasons. One of the reasons we might care to decompose into subproblems is if we look at the alternative, maybe that will be elucidating. So the alternative would be doing the top-down type-driven enumerative synthesis starting from the sketch itself. That's sort of the immediate naive approach. When you do this, however, you're sort of looking for completions of each of these different shapes that we see here. So maybe in exploring a tree, you come across the orange circle, and then the green circle, and then the purple circle, and you're branching out. And as you continue exploring this tree based on your heuristic, maybe you come across the solution, the orange circle, and the blue pentagon. Now, it might be that the blue pentagon is actually correct in this instance, but the orange circle is making the entire solution invalid. So we'll continue our search, we'll reject this option, we will continue iterating through the tree, and eventually we'll come to the correct solution. And this correct solution might be the purple circle with the blue pentagon. However, you note that we now have two separate branches of the tree that both have to resynthesize this blue pentagon again. Sadly, caching doesn't seem to be very effective because we still need to maintain all the intermediate results of here so that we can actually branch out and continue exploring just in case this isn't the actual solution. So by breaking this up into subproblems, we ensure that we only have to synthesize the solution to every single one of these exactly once. Furthermore, in our previous example, we saw that Bob was only using one sketch, one higher order sketch, although that's not necessarily the case. Oftentimes, we don't know which sketch is going to yield a correct and good solution, so we allow the user to include as many sketches as they might care about. Now, when we're dealing with a lot of sketches, you might expect that we need 6 producers here because we have 2 sketches, each of which has 3 holes. But when you do the type inference in the set of examples that we have, because these are sharing the same set of examples, you find that sometimes they actually share types. Both of these sketches actually have an empty square that needs to be filled in. So that we can actually use 5 producers instead of 6. And they'll all feed into the sketches at the same time. So this is also how we take advantage of the producer-consumer model to save on work and improve performance. Okay. Now that we've produced full programs, we need to ensure that they are correct. We do so by ensuring correctness on the input-output examples, but we're still not done there. And to show you why, I'm going to walk through another example. So this is sort of the hello world of MapReduce programs, is doing the word count. This is actually even simpler than the stereotypical word count that you'll see in most MapReduce tutorials because we're not counting the occurrence of every single word, we're just counting the number of words total. So we've got 3 sentences, and if I did my math right, there should be 12 words in there. So when walking through a solution, we'll start off with this sketch because I know that this is how this example is going to go. It'll help. And the first thing we do is map these strings. So we're actually using a flat map this time, which is essentially just like a map, except it's going to produce a list, or a multiset, sorry, and we have to flatten all the multisets after the fact. So this map is very simple. It's just iterating over every single character and replacing it with a 1. Then we're going to synthesize the reducer that takes 2 arguments, x and y, and returns x plus 1. So when we construct our parse tree for the reducer, we evaluate and we get the answer 12. So we found a correct solution, right? This is good, except not quite, because the shuffle phase guarantees that we don't necessarily know which order we're going to be receiving these elements in, and so we don't know the shape of the parse tree beforehand. So an extreme example is the one we already saw, where everything is aligned on the left, and in this case the value evaluates to 12. The other extreme example is a parse tree where everything is aligned on the right, in which case we totally ignore the rightmost subtree, and we end up with a value of 2. This is bad, and we would like this not to happen. So what we do is verification to ensure that our program is deterministic with respect to the shuffle. And it turns out it's sufficient for the reducer to be associative and commutative over the domain that we care about. This is what's called a commutative semigroup. And we have multiple different ways for proving that a reducer is a commutative semigroup. But first, I want to point out that this is a sufficient condition. It is not necessary, or it is not a necessary condition. It is possible to have a MapReduce program that does not have an associative and commutative reducer that is still deterministic with respect to the shuffle phase. However, that usually involves whole program analysis and can be rather difficult. So we focus our efforts on one piece that we can actually tackle. So the first approach that we have for proving that this is deterministic is the simple naive approach of just checking all the possible parse trees whenever we are evaluating our examples. We don't necessarily know in what order the elements are going to come from the shuffle phase, so we check all parse trees and just check equivalence. Now this has some problems, namely that it scales with the Catalan numbers. There's quite a lot of parse trees of any given size. It's actually more than just the simple Catalan numbers because this does not take into consideration the permutation of the leaves in this case. However, empirically we found out that the number of examples that we have is typically very low. So even though this scales exponentially, this is still very, very feasible. However, it's only as good at pruning out non-associative and commutative operators as our examples. If our examples don't ever illustrate this behavior, then we still might accept programs that are not going to be fully deterministic whenever we scale it up and throw more data at it. So with that in mind, for any program that actually passes through our dynamic analysis, we're going to perform a second round of static analysis. Now, for this analysis, we're going to take every single reducer and encode it as a ternary relation in first-order logic. We do this by just assigning the two inputs with the output as a relation. Now, if you were in the verification session yesterday, you may be familiar with a K-safety property. Associativity and commutativity are both hyperproperties, meaning that they need multiple executions of a particular function to prove. Or in this case, they need multiple copies of the relation that encodes this function. Now, associativity is usually a 4-safety property, and commutativity is a 2-safety property. So when you put them together, you might expect that we need 6 copies of our relation, but it turns out we can do it with only 5. We do this by encoding associativity and commutativity in these particular formulas. Now, the commutativity formula is fairly straightforward. We have the relation, we permute the order of the elements, and we ensure that the outputs are equivalent. Associativity is a little bit more complicated, and you'll notice it uses one less copy than you might expect, partially because the very first copy in the associativity constraint is using the output of one of the copies in the commutativity constraint. So by composing these together, we can actually prove associativity and commutativity using less than the expected number of copies. To do so, all we do is conjoin these together and check validity. We just need to guarantee that on every single input and every single possible output that satisfies our encoding of the functions, the formula is valid. So as a quick overview, we've seen how we're actually parameterizing the search. We are looking for a program that is consistent on the input-output examples, and we're looking for these programs by composing API functions and higher order sketches. We perform our synthesis in a producer-consumer model, which allows us to share a lot of work and take advantage of very parallel platforms. And to ensure our solutions are correct and will scale, we have a deterministic verification stage after the fact to ensure that we'll always get the right answer whenever we run our program. Now let's turn to performance. We had a wide range of benchmarks. We had approximately 35 spanning multiple different domains. For example, we had the collected works of Shakespeare, and so some of our benchmarks were trying to synthesize programs that were counting character lines, for example. For tweets, we were interested in things like hashtag co-occurrence patterns. We had Wikipedia logs, and so we were interested in the number of bytes that were transmitted to and from a page on a particular day. And there's a lot of numbers up here, but there's a couple of stories I want to direct your attention to. And the first story is the wall time. This is from when we hit enter on the keyboard to when the solution pops up. And this is not accounting for all the work that's done by the reducers and the consumers. This is actual time on your clock. And you'll notice that, for the most part, all of these programs finish very, very quickly. The Wikipedia filtered takes about 13 seconds, but this is actually the longest running in our benchmark. This doesn't necessarily tell you how good this is, other than the fact that it doesn't take hours and hours to run. So perhaps more informative is doing a comparison. So the CPU time column indicates the total amount of work that's done by the producers and the consumers. Now this other column is the work list time. This is the naive algorithm where you do top-down enumerative synthesis starting from the sketches themselves. This ends up being a frontier search over a forest and can be encoded as a work list algorithm. So in almost every single case, Big Lambda is faster than the standard work list algorithm. There is one instance where this is not the case, but both of these happen to terminate fairly quickly. In every single other instance, Big Lambda is able to synthesize these programs with less total time than the standard algorithm. And in some situations, is able to synthesize them even when the standard algorithm will not do so, and it actually times out. Furthermore, we have a third column in the center, which gives you the number of examples that we typically use. As you can see, for the most part, it's just one example. And remember, these examples are sort of a collection of inputs and the associated output that we expect from our MapReduce program. Usually the math functions end up requiring more examples because it takes more instances to sort of pin down the behavior. They're a little bit more complicated than some of the string manipulation functions in that sense. So another item we had in our benchmark was the Yelp challenge dataset. We were curious about some questions we might be able to ask about businesses and reviews, for example. So one question we had was, which city has the most kid-friendly establishments? So to see if our program actually scaled and could run on a larger system with more data, we handed Big Lambda this set of examples. This set of examples has, as you can see, just 4 elements. Each element just has each element has the city, the business that's associated with it, and a set of attributes that are associated with it. Just by counting up the number of attributes that we see, we can see that Madison has more kid-friendly cities than Dallas, at least on this instance. I don't think that might not actually be true. So after handing this data off to Big Lambda and letting it churn away for a few seconds, we end up with this example program. And this looks actually fairly similar to the program that Bob synthesized when he was trying to count hashtags. We are taking every business, we are pairing up the city that's associated with the business and any instance, if there is any, of the good for kids tag that Yelp uses. From there, we are reducing by key, which means we're taking all the pairs that are associated with the city and adding up the secondary elements. This just gives us a count. And then from there, we can just apply a function which lets us pull off the city that it's associated with the most. And in doing so, we decided to run this on the whole Yelp challenge data set to ensure that it would actually scale up appropriately. And we did get the expected data parallel performance, but we did not get an answer that we expected. It turns out that the most kid-friendly city in the Yelp challenge data set is actually Las Vegas, which is not what I expect when I think of kid-friendly cities. It turns out they just have the most cities, or the most establishments in general compared to everything else in the data set. So proportionally speaking, they may be less, but in actual numbers, they're more. So this is not a problem with our synthesis. This is just a problem with the data set being a little bit limited. In the future, there's a lot more we'd like to continue to do with this work. Specifically, we would like to try and actually optimize these data parallel programs. Usually these platforms like Spark and Hadoop have a lot of various knobs to turn to optimize performance very highly, and currently we're not dealing with any of this. We know this is a research topic that people who focus on these platforms focus on very, very heavily. We'd also like to see if we can automatically parallelize currently existing programs by using them as an oracle instead of using these input-output examples, for example. And with that, I thank you for your attention, and I'll be willing to take any questions.
The fastest. I really liked this work. But I have I guess it's like an initial question regarding the search for the operators and the constants. Say like I'm working on numbers, and what I want to do if it's positive, then I add 7. If it's negative, then I divide by 2. So I guess if you search enough, then you will find that the whole pieces of the puzzle. But it seems like a very large search space. So can you say a bit more on how do you handle that?
So typically, whenever a user is trying to synthesize a program that has constants, they'll know ahead of time what the constants are going to be. Like if Bob is trying to figure out how many times his handle appears in tweets around the world, he'll know to look for the string @Bob. Handling numbers is usually a little bit tricky. Typically, we include just a very small subset. If you're doing something like a histogram, it's very simple to already sort of know beforehand what you want to partition on. And this is something that our tool does not handle very well. What we'd like to do in the future is handle these numbers symbolically and essentially just treat them as normal numbers and do some analysis after the fact to figure out what values they should be taking.
Okay, thanks.
Hi. Looks like great work. It was very impressive that you were able to do this with just one example. I was wondering what the size of each of those examples is.
So the size of each of those examples is roughly in
syntax for the reducer would be better.
Oh, very likely, yes. Most of these reducers in the benchmarks that we saw were of a very particular form, usually some sort of like binary operator like a max or addition or just comparing the two or string concatenation, something along those lines. One of the reasons we decided to do it as such was so that we could maintain extensibility as we're adding on extra domains. We didn't want to try and predict what future solutions would look like, but yes, it's very likely that we can guide the search towards those associative commutative results better.
So I also have a question.
Mm-hmm.
You mentioned this 30
They usually work very simple. So typically the verification per example was only ever run once or twice, just because it tends to be in the benchmarks that were selected that the reducers happen to be very simple, and we'd come across them first in the search and didn't have to do much exploration after that.